If, as he said already, I will give a or try to give you an overview about a completely different type of supernova, the Type Ia supernovae that are powered not by gravitational collapse but by nuclear burning, so thermonuclear supernovae. And so this overview is mostly based on stuff we have done in the what once was the Type Ia supernova group at the Max Planck Institute for Astrophysics in Garching, but where most of the people are, or a lot of the people are now in other places, and it's like just scattering more and more. But yeah, started all at MPA. As an outline, I will first give you a brief 2-3 slides summary introduction to Type Ia supernovae, that you have like a rough idea what I'm talking about later if you don't have that yet. And then in most of my talk, I will try to give you an overview about how we actually model these supernovae from like a first principle approach. And in the different parts where we use different codes, I will try to address what actually the approximations are that go in there, and what the limitations are that we face at the moment. And I will try to convince you that we are mostly, or most of the limitations of the limitations in physical models are actually introduced by limitation in like computing power, and that the main advantage of more computing power in the future will be that we can get rid of more and more of these physical approximations and actually get much more accurate models in the future. Okay, so Type Ia supernovae, as I said, they are thermonuclear explosions. Why are they interesting? There are three main points. The first are they are important tools for cosmology. So they are used as standardizable candles to measure the acceleration of the universe. You all know that. An important note here is that the whole cosmology game with Type Ias is so far purely phenomenological. So our first principle models don't really have anything to do with that yet. They are not precise enough yet to actually use them to improve the cosmological estimates. But it's one of the things we at some point really want to do. The second point is they produce a large fraction of the chemical elements that are not produced in core collapse supernovae. So at least 50% of the iron is supposed to come from Type Ia supernovae. So if we want to understand the chemical evolution of galaxies in the universe, we have to understand Type Ias. And then by itself, they're actually quite interesting because of all the thermonuclear burning and under degenerate conditions and so on. This is basically a physical regime that you only have in these objects. Okay, so what do we know about Type Ias? So we from observations of light curves in different bands from spectra and from remnants, we actually infer that they are thermonuclear explosions of carbon-oxygen white dwarfs. One of the reasons that we are quite sure they are not of core collapse origin, but they have to be powered by thermonuclear reactions, is that there is no compact remnant in the remnants of Type Ia supernovae, so there is no neutron star or black hole, so the energy can't come from collapse. However, in contrast to core collapse supernovae, there is no detection of any progenitor system yet. So there is a large number of upper limits, and with the recent supernova 2011 FE that was quite close, actually all these limits were basically got much better, but they're still only limits. So we have no detection of the progenitor system before the explosion, or any indirect detection of anything in the progenitor system where we are sure that it's from the progenitor system in the explosion. So the two main questions are, what are the main progenitors? Maybe there's more than one type. This question mainly asks for the mass of the carbon-oxygen white dwarf. So we are quite sure that there are carbon-oxygen white dwarfs, but the main question is the main thing that explodes there actually a Chandrasekhar mass white dwarf, or has it less mass than a Chandrasekhar mass? And then the second, as equally important question is what actually causes the explosion. And so we are also quite sure that this is that they have to be in a binary system, and somehow the companion causes the explosion. But we are not really sure yet how that actually works. And then the ultimate goal, of course, I already indicated before already. The ultimate goal would be to have first principle, enough precise enough first principle models that we actually can identify individual explosions with individual models from a specific line of sight or something. Because then we, in principle, could directly infer, for example, the brightness of the explosion just from observing the spectra or so on. Just for if the models would be good enough, we could do that on a single object basis. But we are still far away from that. But yeah, that's what we want to do. So how do we actually model those objects? So this is done in several steps. The main reason for this is that in the different steps, the important physical processes and the scales, the time and length scales that are important change a lot. So we split that in different parts. The first is we have to kind of start with a progenitor system and model how this actually leads to the ignition of a flame in the carbon-oxygen white dwarf that's then exploding. The second part is the actual explosion. So we have a thermonuclear burning and we have to model that accurately to get the right structure of the ejector. We then, in a third step, that's usually done in post-processing, have to get the information from use the information from the explosion simulation to get really detailed nucleosynthesis, because we really need to know like the isotopic abundances of the ejector. And then we use radiative transfer simulations that model basically the ejector that are flying apart for several weeks to months to obtain synthetic observables, spectra and light curves mainly, and then we can compare those directly with observations. Just as a note, all these simulations are run in full 3D, because there's basically none of these models has any intrinsic symmetry that you can really use. And it turns out that if you don't do that in 3D, actually you already have quite some errors. Okay, now I will go through all these parts in more detail. So the first one is how are actually the progenitors modeled. So this is one thing we don't really do within the API group, but this is done by other groups. This is an example of Nonaka et al. So this is the question: what actually happens that then leads to the ignition? And this is an example of a Chandrasekhar mass white dwarf. The basic idea is that this Chandrasekhar mass this white dwarf accretes material from whatever companion until it reaches the Chandrasekhar mass. Then it starts burning in the center, but the nuclear burning is not a runaway yet, but the energy is transported away by convection. But the temperature slowly rises, and at some point the convection is too inefficient to actually transport all the energy away, and you just get a runaway and you get ignition. So from this simulation, here you see this is a slice through a white dwarf. The red stuff is stuff that's moving outwards. The blue stuff is moving inwards. Here's the center of the white dwarf, this black dot, and the green dot is where in this simulation they actually reach ignition. Okay. So this has been run with the Maestro code. The resolution is about 2,300 cubed, and the effective resolution. And this whole thing has to be run until you actually reach ignition for like 3 hours of physical time, but with time steps of like 10 to the minus 2 seconds, so you need like 10 to the 6 seconds. Fortunately, the code scales to at least 10 to the 5 cores for this simulation, so you can run that in a reasonable time still. The main limitations here are probably that there are only like there's basically like less than a handful of those simulations yet, and this is basically they just saw this like the most simple configuration. There's without rotation, without any magnetic fields and so on that could change the like the nature of this convection, and then could change the outcome potentially. So here we probably mainly have to run more simulations, and yeah, a little bit higher resolution would probably help, but it's not clear whether this is the essential point. So for a different progenitor system, this is for a merger of two massive, or of two white dwarfs, carbon oxygen white dwarfs that is below that are both below the Chandrasekhar mass. So what happens here is that you actually you have this binary system. They are orbiting around each other, and at some point they come close enough to that you start mass transfer. And in this particular simulation, we actually incorporated the helium shell that you always have on top of carbon oxygen white dwarfs. And what you see then, if you follow this for like 10 orbits, that because of the accretion, the helium shell is actually heated up quite a lot. And at some point then you ignite a thermonuclear detonation in the helium shell, basically by the accretion, even before sometime before the system would actually merge. So this particular simulation has been done in the moving mesh code repo that we heard about already also. A similar kind of simulation, or similar simulations have also been done in SPH before. This is only the latest one and also the highest resolution one. Highest resolution here means that it has about 2 × 10⁷ cells. Like the mass resolution of the cells is here 10⁻⁷ solar masses in the white dwarfs, and an increased 10⁻⁸ or lower 10⁻⁸ solar mass resolution on the surface, because there's where most of the action happens. So we decided to run with higher resolution there. One thing that's still quite approximate here is that the nuclear energy generation is done only with a 13 isotope alpha network. The main reason for this is that we can't really afford more in this type of simulation, and also this requires about 500,000 time steps just to run 10 orbits, and yeah, that's a few million core hours. There are two main limitations here. First, we would really like to run this at higher resolution, and the second thing is, once we actually have that at higher resolution, we can already resolve smaller accretion rates, and so we basically could start earlier and see whether this significantly changes the picture, because basically the point where we start to run the binaries with the binary interaction is given by the amount of basically limited by the by the accretion rate that we can actually resolve. Doesn't make sense to start when there is nothing happening between the white dwarfs. Okay, so now basically we have a progenitor model, and we kind of have a point where it ignites. So what we then do usually is, we run the explosion. We have a different code for that. This is the MPI supernova, Type Ia supernova code, or Leafs code, if you ever heard that name before. In this code, we then typically put in the ignition at the point where we think the ignition happens. So this is a much more simple code. It's usually on a uniform or hybrid grid. And the main point of the code is to do the best job we can with the nuclear burning. So it tries to model the nuclear flames very accurately. And what you see here is such an explosion of a Chandrasekhar mass white dwarf. The white surface is the flame surface of the deflagration, the initial flame that starts that burns subsonically, and the blue stuff is the surface of the detonation that is ignited later once basically by turbulence that's caused by this deflagration. So as I said, the main thing is to get the evolution, so to get the nuclear burning right, and there the most important thing is to get the nuclear energy generation right. However, for typical simulation for this is 1,000 cubed or so, and also there we can't really, we can't afford at all to run a huge nuclear network. So we either have a small nuclear network and try to tune this to get the energy generation as correct as we can, or we have some tabulated values for the energy generation in the first place. And usually, mostly, as for this code, it's tabulated, and we use a level set approach to track the propagation of the flame. But there has been done in other codes differently, so you could also use Flash or Repo for this type of explosion simulations. So yeah, the main thing we would want to improve here is the precision of the nuclear burning. The best thing would be if you just could afford like a huge nuclear network with like a few hundred isotopes running in parallel and really give us the like correct energy generation in for every cell. But yeah, so at the moment this is like completely impossible. But if we have a much more, if we have a much bigger computer, we may actually be able to do that at some point. Also, this is if you're completely dominated by your nuclear network, it's actually quite easy to paralyze because yeah, you don't have too much of an imbalance. The other thing is that we still want to go to higher resolution. So for the scale, so white dwarf is like about 1,000 kilometers in or a few thousand kilometers in radius. The physical width of a carbon oxygen flame is about like centimeters or so. So it's completely hopeless to resolve. However, helium detonations, which in some models then later trigger carbon oxygen detonation, are of the size of like a few to 10 kilometers. So this is actually in reach that we can really resolve the structure of helium detonations in these simulations. Okay, so once we have the explosion, usually we run this explosion until the nuclear burning has ceased completely and everything is flying apart, so there's nothing left over. And then we run it like so that usually takes like 1 or 2 seconds, and we run it another 100 seconds until everything is on homologous expansion and like dynamically in the ejector, nothing is happening anymore. What we then, as I said before, need is really the detailed isotopic abundances. For this, so basically at the moment we can't afford to do that directly in the simulation. So what we usually do, we have of order million Lagrangian tracer particles that record trajectories of temperature density, many temperature density, and then we basically use a huge nuclear network and post-processing calculate the isotopic abundances of these Lagrangian traces. Yeah, just note that this 10 to the 6 million tracers on a 400 isotope network is already quite expensive, and this is significantly less than the resolution of the actual explosion simulation, what we can afford here. And yeah, so the main improvement here would be well, we can increase the tracers a bit, but this is like, there are all kinds of other issues if you use tracers instead of doing it directly in the hydro, which is like problems with mixing and so on. So the main improvement here would be to, at some point, just get rid of this step completely and figure out what the minimum nuclear network you need that gives you all important isotopes that you can run directly. It's probably of the order of like 100 plus isotopes, and just do that in the hydro. Okay. So the last step then is probably the most expensive one, even though the other ones weren't cheap either, is that we do radiative transfer on the ejector with the isotopic abundances. The main problem here is that this is a multi-physics problem. So one of the problems is that most of the ejector for most of the times are actually optically thick. So this is also why usually it takes like 2 weeks or so until such a supernova basically reaches its maximum in brightness. Although everything you see is powered by decay of radioactive elements, mainly nickel 56, and the decay is most of the decay you already have like at early times, just because it's decay. But this is so basically that they just make like gammas and positrons, and then they propagate for 2 weeks through the ejector until they actually most of them can escape the ejector, and you see the maximum brightness. The opacity is dominated by atomic lines. So to do this correctly, we really have to accurately model the interaction of photons with a lot of lines, and so we think that for accurate results you have to have a line list of at least like 1 million lines or so. But also there we would like to use a lot more, and we are not completely sure what the systematic effects of only using 1 million lines are. And the other thing, so that you have to do the whole game in 3D, because usually the ejector structure is actually quite complicated, and also the density and composition. So the code we use for that is the so-called ARTIST code, is written by Markus Kromer and Stuart Sim. And this uses like Monte Carlo energy packets, and really computes the the propagation of these energy packets and the interaction with all kinds of atoms, and then until they finally leave the ejector. So for a typical 3D explosion run, we need of the order of 10 to the 8 of these energy packets, and they have of the order of 10 to the 6 interactions before they actually leave the ejector. So this is really a lot of computation that we have to do there. The code, fortunately, scales to at least 10 to the 5 cores. The at least is there because that's like the biggest machine we've run it so far on, but it's probably it will scale without too many problems to 10 to the 6 or maybe even more. The main reason here is that the approach we do is we just save the whole grid, where we save the density and the composition on every task, on every task. So we basically can really concentrate on the propagation of the energy packets, and we only have to synchronize from time to time. Okay, and the improvements, we want to do more packets, more lines, and also there are a few approximations in there that we want to lift further. Okay, so now where are we at the moment? So this is a comparison of two models of a Chandrasekhar mass explosion and a merger of two white dwarfs compared to the spectra of 2011 FE, which was this really nearby but really well observed Type Ia. And so the thing is that so they are not bad, both of them. The Chandrasekhar mass explosion is good at like very early times, and then around maximum here, it's like it has clear deviations. The merger is not too good at early times, but fits very well around maximum. So the main argument I would make is that basically none of these models are actually like precise enough yet that we can really make a strong statement that either of them is like right or wrong. And the other thing is we clearly need more models, so we only have a very small number of really detailed models where we run through all the pipeline in like the best we can, just because it's very expensive. Okay, to my conclusions. So we basically have a complete pipeline to model Type Ias from the progenitor model through ignition, explosion, and so on to then obtain synthetic observables. Unfortunately, the accuracy is at the moment not sufficient to really identify individual models with individual explosions, or generally with a subclass of explosions. Most of the accuracy is probably, most of the limitations of accuracy are probably by physical approximations we have to make on in the pipeline at the moment, and not necessarily by simple things like just going to higher resolution. And yeah, more computational power will hopefully allow us to lift a few of these approximations and get significantly more accurate results.